If you find these videos helpful, please consider supporting AddOhms and the Bald Engineer on Patreon. Hello, my name is James and welcome to a Bald Engineer live stream. We've got a bunch of stuff we're going to do today. I had wanted to start a little bit sooner, but here we are. So first, let me say hello to everybody in chat. It looks like you guys are having fun playing the trivia. Let me know that you can hear me okay. Just say your favorite component. Let's go with that for the mic check today. Oh man, that's not good. And let's see. That's looking good, that's looking good. Let's kill this so I can keep moving. 555. Perfect. Yeah, so we're going to do 3 things today. Just realized I don't have the third one set up. Let me grab this real quick. I had wanted to just do one topic, but a couple of things I ran into a couple of issues. Turns out I broke the LAN port on my scope, or it appears only one particular LAN cable works on it. And so that's why I started the stream late today, because when I moved the scope over to here, it stopped talking to the LAN. So got that figured out. Because of that, I'm going to modify what we're going to do today just a little bit. Mr. 2M, I said to say your favorite component, so you said your favorite component. Like that. Good job. So let's look at what I want it to get done today. And I've got stuff all over the place now. Let's go to the B-roll. So there's 3 things I want to work on. So this board you might recognize. This is man, that is crooked and that's going to drive me crazy. There we go. That's better. So this is the MOSFET board that we designed a couple weeks ago. Then we populated it on a live stream a few days ago. I have the current sense resistors, so I want to put that in and then make a couple measurements with it. I did realize I've made a mistake. It's the same one I made with the op-amp circuit, but we're going to go ahead and try something out on it anyway. I also need to test, this is a 12 volt boost converter that I made for a E14 project, and I'm going to need it again for another upcoming project. So I need to see how much current I can get out of it before it gets really noisy. So we'll hook that up to the scope and see how noisy that gets. And then if we still have time, one thing I would like to test is let me grab the case. This is a LNA, low noise amplifier, from RTL SDR blog. It's meant to be used with a software-defined radio, which I've got a couple of those. The thing is, when I use this bias T adapter, with this board, it doesn't seem like this amplifier is turning on. And so one thing I want to do is I want to hook it up and see if anybody recognizes what I'm doing wrong. And then if what I'd like to do is hook this up to my RTL SDR and see if we enable the bias T, if we see the amplifier do anything. And so what we'll probably do is swap the scope out for the spectrum analyzer, or maybe even the nano VNA. Today we're just going to do it with the spectrum analyzer because I don't know the nano VNA well enough to trust that. So yeah, it's not, I don't think it's an impedance matching issue. I've never used one of these bias T boards, so I don't know if I'm doing something wrong, but when I apply a DC voltage, I'm not seeing this turn on. So that's why I want to try it with the SDR, because it's supposed to work with the SDR's bias T. And so if that doesn't work, then I know there's something wrong with this. If it does work, then we can troubleshoot that a little bit more. So let me get this out of the way so we're not messing with that. So the first thing we're going to do is work on the MOSFET board, which means we need to solder on the current sense resistor, which I did finally receive. So excuse me for one moment. Okay, mucho bettero. Cheers, everybody. Happy Easter if you're celebrating Easter. Happy Sunday if you're not. And I hope everybody has a good week this week. Let me drink some tea and then we'll be ready to go. Okay. Let's see. So we're going to do some soldering. So I need to get some solder stuff. BA55 UK, thank you for the follow. By the way, I know many of you are watching on YouTube right now. I just wanted to mention that I am starting to transition live streaming over to Twitch. So if you want to continue to see all of the live streams, then you'll need to head over to twitch.tv/baldengineer. What I'm probably going to start doing is during the week, I will be doing streams. I'll continue to do YouTube streams. And then on like Sunday mornings, I may start switching over to backwards. During the week, I'll be doing Twitch streams. And then Sunday morning, I'll do a couple more YouTube streams. But I'm going to kind of push everybody over to Twitch for the live streams. Now, that doesn't mean I'm going to stop doing stuff on AddOhms. I know I haven't posted too much recently. What I plan to do is edit the live streams and then post those onto YouTube. And so you'll still get to see the stuff that's going on, just may not be in real time. El Napo, thank you for the follow. Alrighty, so we're going to do some soldering. So I got my fancy solder jig here. I'll fix the cameras here in just a second so that you can see exactly what we're going to be doing. Let's bring this out a little bit, put this to about here. Get these guys out of my way. In fact, I should just do this. Should unscrew them, but okay. Going to try and follow. Let's see. AJ Mole, thank you for the follow. All right. Let's see. Soldering iron is heating up. And we're going to put this board into, let's see, I need to get to, okay. So when we soldered this the other night, I realized that trying to get into where the current sense resistor was is going to be an issue, but I decided to do the majority of the soldering anyway. So the goal here is, grab my plastic thing, my plastic pointer, if you will, is, if you can't be with family, you can at least be here. That is true. So the goal is, this will be a current sense resistor. I just realized some of you may not even know what this circuit is. So let me review the circuit really quick, and then we will we'll get to the soldering. So let me pull that up. Okay, let's go here. So we designed this board. It's a MOSFET test fixture. There's a couple of MOSFET measurements that I want to make. In fact, one of them is for an upcoming AddOhms video that I've been working on for quite a while. It's a follow-up to the original MOSFET tutorial. And so the way that we designed this board is it has a couple of pads for a pull-up, pull-down resistor as well as a capacitor. The idea is that we may want to design a RC filter to do some soft starting with the MOSFET. There's a pad for a current limit resistor. Now, one of the boards I have today has a 0 ohm resistor and the other has like a 2K resistor. And that's what we're going to end up measuring. The whole point, the primary reason for this board was I wanted to talk about why do I recommend a current limit resistor for a voltage controlled device like a MOSFET. And so to show that, I wanted to put in a shunt resistor, which is a current sense resistor, and then we'll use a differential scope probe to measure the voltage across just this resistor. The reason we do that is because then we can know what is the current that's going through the gate signal. Now, I did realize a problem, and I'll come back to it when we get to the scope measurement, but I overlooked something when I put this in here. There's also a flyback diode on the back side, which is probably too small to actually be useful. If I decided if I need it to drive an inductive load, I would just put it into the screw terminals. And then we also added an LED, which I have a solder pad so that we can remove the LED from the circuit in case it's messing up our current measurements. Hey Yasser, yeah, making very good use of quarantine. So Ken's asking the value of C1. So I just want to point out that R1, R4, and C1 are not populated on this board, and they're not going to be for today. This is for if I want to later on do a measurement where we are creating an RC filter to purposely slow down how fast the MOSFET turns on or off. So for today's measurement, these three components are sort of don't cares. They're not going to be in there. I have a current limit resistor, and we're going to add the shunt resistor right now because I finally have them. Okay, so let's go back to our soldering job. And first thing I want to do is throw a little bit of flux down. So let's get that going. All right, so question I like to ask, since I'm sure many of us are in isolation mode or not able to go out and do anything. Oh, there it is. Kind of in isolation mode. What kind of projects and stuff have you been working on? I'll start outside of electronics, obviously, and doing live streams every other day, or almost every other day. I've been playing the Telltale's Batman game, the first one. I guess there's two. I just realized there was a second one, The Enemy Within. Not that one, but the first one. And I've actually really been enjoying it. It's, if you're familiar with Telltales, they're like, they're really story-driven, puzzle kind of solving kind of things. It's not really an action game. It's almost got like a Dragon Lair quality to it because of the action or button action timing. I don't know how to call it. But anyway, that's what I've been doing outside of electronic stuff. So what have you guys been up to? Okay, let's get that onto here. And then let's get this onto here. And now let's grab this guy and take back off some of the solder. I'll leave the other on, although I just realized I need to go this way. All right. Movies, virtual hangout, Netflix. Yeah. Anything cool to watch on Netflix? I don't actually have Netflix, so I don't watch all of the shows there. But yeah. So somebody was just asking, what's the PCB do? I just finished explaining. It is a test fixture for MOSFETs. The primary measurement that we're after is I want to show how much current actually goes through the gate of a MOSFET when you turn it on. Most people think of the gate of a MOSFET as zero current, and that's not entirely true. So that's the purpose of this circuit, is to give us a chance to measure that, as well as outside of that measurement to be able to measure the voltage drop of the drain and source when the MOSFET's being used. And to allow us to create what we call a soft start driver, a very, very simple soft start, where we add a capacitor on the gate to slow down the rising edge. Now that's not always ideal. In fact, sometimes it's a very bad thing, but it'll make for cool measurements later on down the road. So it is just a MOSFET test jig. And we designed it as a live stream about a week ago. Board came back on Thursday or Friday, and then we did a live stream where we actually populated the rest of the components. I also have another transistor, but I'm not going to populate that today because, like I said, I figured out there is an issue. Okay, so this board I think is ready to go. Shoot. I just realized I never measured the value of the resistor. That's okay though, because I'm not after the specific current. Let me think. Can we measure that really fast? I don't know how to do... I don't think I have the probes I need to do a surface mount. And that's okay, because we're not after the exact amount of current. We just need to create a voltage drop across that shunt resistance. And all I'm after is I want to show you guys what the waveform looks like and the order of magnitude. So I think we'll be okay. All right, so this is my other board. This one has a 0 ohm resistor. So basically it's like as if you did not have a current limiting resistor. What would it look like? So that's what we're doing with that one. The other one has a relatively high resistance. It's like a couple of K ohms. As repeat viewers will know, I have an ongoing saga with I can't seem to keep 1K resistors around. I thought I had 1K surface mount. Well, first I thought I had 1K through holes. I found the empty bag, but no resistors. And then I tried to find the 1K surface mounts and can't find those either. So boo on that. Hello, Romania. Ah, cool. You helped a friend move. I'm going to be moving soon. You want to come help me? Just kidding. I'm going to hire movers. Altered Carbon. Yeah, actually, I watched about half of that one. I didn't get all the way through it. As with a lot of shows, if I can't finish it on, say, one plane flight to Europe or not, then I don't usually get through it. And that one, I had a hard time watching that one on a plane just because of the violence and the sexual nudity and stuff like that. I don't really like it when naked people show up on my screen while I'm on a flight. I think it's just kind of awkward. Can you please add 720 for the stream? Sorry, I don't have any control over what Twitch outputs. I output at 1080 and then then they do the down conversion. I do think that I don't think I have a priority on down conversion, so maybe that's why they're not offering the down conversion yet. But yeah, sorry about that. Wait a minute. There's some weird corrosion around this MOSFET. I don't know what happened. Interesting. Let me see if I can... Let's see. Yeah, so you can actually see this is what's worrying me, is that this formed just over the last couple days. Can I just chip it away? Okay. Maybe it's just leftover flux residue and I didn't clean it off very well. Yeah, it looks like it went away. Let's grab a Q-tip. That's what I meant to do. Just add a Q-tip and clean this up a little bit more. And then that's the gate and drain. Okay. Okay, cool. So that's on. That's in place. That's why you get the window seat. Yeah, I don't like the window seat because I like to get up and pee. whenever I want. And I feel like as soon as I sit down at the window, I have to go to the bathroom. And so it's always frustrating. Okay, how are we going to drive this now? Step one, let's get some focus so you guys can see what's going on. So one of these, so this one has the 0 ohm resistor, this one has the 2.2K. So let's start with 0 ohm. And what I want to do is let's set this up to drive the MOSFET. How do we want to drive it? Why don't we try to drive it with an Arduino? Okay. So what I'm going to do is use my electronic load, which I'm sorry, but it's going to be super loud. I can't help it. It's got a ridiculous fan in it. So what's going on? So right now we're working on this MOSFET board. This is a MOSFET test fixture. We just added the current sense resistor. So now we're going to hook it up and just make sure that the board works, meaning we can turn the MOSFET on and off. And then we're going to make some measurements across that MOSFET. So let me turn on my electronic load and let that just make a boatload of noise. Oh, you know what we can do? I need to switch my plugs over. There we go. Yeah, sorry. Like I said, it's loud fan noise. Why do you use Eagle? Well, I don't. I use KiCad. I haven't used Eagle for 5, 6, 7 years now. I looked at Eagle 9 when it came out, and I thought they had made some nice improvements, but I switched full-time to Eagle. I'm sorry, switched full-time to KiCad 5 or 6 years ago. Let's do this. Oh, why did I do that? That's not good. All right, so now we need, how do I want to connect that? I got an idea. This normally doesn't work well, but it's going to work great today. Nope, that won't work. What I was thinking about is I've got these cables that come apart very easily, and we can use those to go into the screw terminals. That way, nope, that's not going to work either. Okay, that's what we'll do though. Let's get this one. And this one. Okay, so we'll need those. And then I think we'll be able to get away with just jumper wires for the other stuff. So this will plug into here. And this will plug into here. And I know you can't see that too well, but I'll show you what I've got going on up there in just a second. Have you ever tried Circuit Maker Studio? Yeah, I've never tried any of the Altium stuff. I've had 2 interactions with Altium salespeople, and they were complete jerks to me. So unless something changes, I will probably not be doing much with Altium. You know, it's just, I feel like if you're trying to get somebody to buy your product, you should, I don't know, not be a jerk. Okay, what I'm looking for is like a pin or something that I can stick into. Yeah, why don't I just try header pins and see if we can get those to stick, because I'm not going to drive a ton of current in this measurement. I'm just trying to do, all we're doing is testing to see if we can turn the FET on and off. Oh, you know what I thought of? I know. You know what we need? We need an LED. I need something bigger than an LED. Let me think about that for a second, because you're probably not going to be able to see when this turns on. but I'll think of something while I'm hooking this up. We'll come up with something cool. So I'm going to stick this in here, screw that down. Okay, and then we'll stick this one in here. And we'll screw that one down. And let's see now, this is going to be drain. We'll connect. So wait, what am I doing? I need another power supply is what I need. Because I need to go, nope, you guys can't see that. What I need to do is go from power to the thing. Okay, I just wasn't thinking ahead. So we'll go from my power supply into the load, from the load into the board, and that's going to go to the drain, and then the source is going to go back to the power supply. Ah, come on. Okay, do this, and then we'll do this. And then this will go back into my power supply. Okay, now I know you guys are like, what the heck is he doing up there? So let me show you real quick what we've got going on. Okay, why'd you turn back off? All right, so on the left is an electronic, oh, you still can't see that, can you? Huh. Ugh, screw, oh. Here we go. So on the left is an electronic load, and on the right is my power supply. And so the power supply is connected to the load, and then the load is connected to my MOSFET. And so this is going to be called a low side switch because the MOSFET is then connected to ground, back up to the power supply. So all we're doing is I'm using this electronic load to simulate some kind of load because I want to be able to see if we can turn the MOSFET on and off. Okay. So that's hooked up. We'll turn on power. And that needs a power cord. Shoot. Okay, well that's a problem. The reason I want to use the electronic load is because if I screw something up and we get in something could be blown up, we're much more likely to be safe. So I'm going to set this thing to be mode resistance, and we'll have it be 100 ohms. Okay, that will be fine. We'll turn it on. And there is 5 milliamps. What? Oh, it's because it's open. Okay. Now we need an Arduino. Actually, that's not going to work either. Shoot. Well, all right then. Okay, now I got it. I ran out of USB ports. That's what was kind of throwing me off. But I got a solution. Okay, so we're going to grab a couple of jumper wires. That looks good. That looks good. And we're going to go from, let's say, pin 3, because I'm going to want a PWM pin. And we'll go to gate. And then we're going to go to ground. And yeah, I'm using a red wire for ground. Uh-oh. We'll survive. Interesting. Okay. So, got our Arduino, got that. Now we need a to clean up our workspace, because now we need to program the Arduino. Okay, let's go laptop overhead. Nope. Yeah. So let's fire up Arduino. All right. Yep. I know you're complaining. That's fine. I'm okay with your complaints. So how many ohms are you going to add? We're actually just going to add unsigned. Oh, that's not good. Let's fix that. Well, it's right there. Laptop B-roll. Interesting. Why is that? That's messed up from last night, but I don't know why it's doing that. Let me play with, so scene from, oh, maybe I opened the wrong one. Scene from laptop. Edit, transform. Shoot. What is going on? I guess I can just move it over, but I don't know why it's offset the way that it is. That is very strange. Okay. Unsigned long, previous millis. Unsigned long, interval. Let's go 1000. And let's do const byte. MOSFET pin. MOSFET pin is equal to 3. All right, and then we'll do pin mode MOSFET pin output. And then down here, we'll do if, let's do unsigned long, current millis is equal to millis. If current millis minus previous millis is greater than or equal to the interval, then the first thing I will always make sure I do is reset the clock. And then what we want to do, let's do a Boolean for MOSFET state is equal to false. Let's do this. Digital write, MOSFET pin, MOSFET state. If MOSFET state equals true, then MOSFET state equal false, else MOSFET state equal true, digital write, MOSFET pin, MOSFET state. All right, so unless I've made a mistake, let's make sure it compiles, and then I'll explain what I think it's going to do when I start running it. Just full screen has an issue, I guess. No, there's an issue with the OBS configuration from when we were playing with the Apple II GS, and I just can't remember what I changed. Because I offset the screen for that stream so that the 2GS was centered away from the chat. All right. Okay, so let's ignore these for a moment and just come in. So we turn on, we set our MOSFET pin to output, and then I write to that pin the value of the Boolean MOSFET state. So instead of directly doing high and low for the digital write, I want a state variable so that I can, I just like to use state variables whenever I'm trying to change something so that I can check that state somewhere else in the code or change it somewhere else in the code. And in fact, I'm gonna make this one change. Now I think about that, maybe this will highlight the point. So then we come in and then we get the current timestamp from millis. We check to see if at least 1000 milliseconds have passed. This is the way you use millis. You don't reset it. You just compare the current value to a previous value and see what the difference is. By using this subtraction, we never have to worry about millis rollover. Now, in this experiment, it doesn't matter. We're not going to be doing this for 47 days, but always good practice. So then I check my state variable. If it's true, I set it to false, and then if it's false, it'll get set to true. I reset the counter. This is that point. What I meant by this is we take the current value of millis, we stored in previous, and now we can compare the next value of millis to see when there's a gap of 1000. And then I just constantly within the loop keep writing out to the MOSFET pin the MOSFET pin state. Again, the reason I do this is because I might call some other function and let it modify that state variable, and then it gets updated automatically without having to call digital write in a bunch of places. So anyway, that's how I do it. Hello, Kimston, how you doing? I totally forgot to check to see if it was on the right COM port, and it looks like it is not. So port, yep. So let's go COM3, upload that. Okay. Interesting. I hooked up something wrong because the MOSFET I can see it's switching on and off, but my current is pretty high. So let's just go here. Let's see if I can turn this in a way that you'll be able to see it. You can't really see it on the camera. I can see it, but that doesn't really help you guys, does it? So if you look closely, there's an LED right here. This is our gate LED, and I can see it is flashing at about a rate of 1 per second. So that's good. And Huh, that is strange. Because what I'm seeing on the load, is the MOSFET's never turning off, even though it should. Let's double check the data sheet real quick. Did I make a mistake? No, gate drain source. Yeah, okay. So the MOSFET is definitely going to ground. When it goes to ground, then VG. Oh my God. Oh, James. Really? Really? Okay, let me see if we can, we'll play a little game. Well, you can't see the full setup, so I'll just tell you what I did wrong. I forgot to connect the Arduino ground to my power supply. So we're effectively floating at the moment, which is why I'm getting a strange behavior. So let's turn power off for while I do this, and then let's connect ground. I'm going to move this one over here. And then this one I'll connect to here, which is the same point. So now my Arduino ground is connected to my power supply ground. Now let's see what happens. Okay, so this is what I was hoping for. Now we've got it. So let me switch back to my other camera. So on this power supply, or I'm sorry, on this electronic load, so this is pretending to be a 100 ohm resistor. And what we can see is every second it turns on and then turns off. And it's because our MOSFET is now turning on and off correctly. And so it's causing the load to suddenly draw either 100 milliamps or no amps. So this is exactly what I wanted to see, is that the MOSFET is working correctly now. Okay, makes sense? Cool. Also, it sounds like a, what do you call it? A turn signal from a car, because it's just blinking at the moment. Okay. Okay. So now that that's working, I gotta think about what I want to do for the next trick. Because I think I need one more power connection. Hey, Defense, thank you for the follow. Okay. So we can at least do that so we can see the LED. No, can't get there. Okay, so next, let's hook this up to something interesting to look at. Now that I know that the board is working correctly. So let's move this out of the way. I'll unplug the Arduino for the moment, turn off the power. Let's just hook it up to, what do we have that is high current and interesting to look at? Nothing that is readily accessible. Okay. Okay. Nope, that's not going to work. Okay. I guess we could keep using the load. I just need to get another power cord. I wasn't planning on running out of power cords today. So what I'm going to do now, let's go ahead and just get straight over to the scope and take a look at, come on, okay, it's booted, waiting for it to connect to the network. Okay, it's connected. Let's go to 10.11. Let's go laptop and overhead. We'll do laptop and me for the moment. Okay, so we're on the scope now. And then what I want to do is get my differential probe and show you the problem I realize I'm going to run into because I didn't think ahead when I designed this circuit. And it's not actually I didn't think ahead, I wasn't thinking through what we were trying to do. So if I try to hook this up and I plug this into our current sense resistor, which was the original idea. So I've taken this probe and it's plugged into our, basically the points we had across the current sense resistor. And we're going to look at that on the oscilloscope. Let's turn on the MOSFET and then turn on the Arduino. The electronic load is switching, and here I see the problem I thought we were going to have. Yep. So all we see on the scope is noise, and the reason we see noise on the scope is because the current sense resistor is 40 milliohms, and the current that's going through it is not enough to develop a voltage. And I should have realized that, and I didn't. So we're going to have to get a different current sense resistor. But in the meantime, what if we look at the gate and just see if we can see it spiking at all. I'm going to hook this up. All right. And let's go into normal mode. And it looks like we're getting a little bit of noise. So let's do a, let's go into trigger and turn on noise reject. Okay, cool. So now the scope is updating every single time we trigger. Do you recommend any type of IC or circuit to generate a clock around 170 megahertz? I don't know. If you come hit me up on Discord, I have a, there is a SI, was it Silicon or SL, Silicon Labs chip that might work. Otherwise, use a low frequency like 10 megahertz and a PLL and not divide it up, multiply it up. Okay, so what I had actually, yeah, there we go. Isn't that interesting? Oh, I can't believe that actually shows up. So here's a interesting thing that's going on. Let me back up and explain what we're looking at the moment, because it may not be all that obvious. So right now I'm looking at the gate signal of my MOSFET. And when we think about a MOSFET, we think of them as voltage controlled devices. And so by we think of it as you apply a voltage and then the MOSFET does something. What people tend to forget is that the gate of a MOSFET is actually a small capacitor. And what we end up doing is you're actually charging up that capacitor. You actually have to charge that capacitor up, which causes a small amount of inrush current to occur, and then it goes down to zero, just like a capacitor would, because it's very, very small. The intention of this board was to measure that current across a current shunt or a current sense resistor. What I overlooked is the resistor value I picked is way too small for this probe to pick it up. Now, which board are we looking at? Let me make sure. Yeah, so this is the 0 ohm case. And so what I'm doing now is I'm probing on that gate signal. And remember, our Arduino is just turning that signal on and off every second. And so you would expect the signal to go from, let's show you my mouse, you would expect it to go from 0 volts to 5 volts almost straight up. But look at what's actually happening on the gate is we get this little bit of a ring, and then there's this plateau, and then the capacitor charges up. And this is why I wanted to build a test fixture for the MOSFET, because I wanted to show with no gate resistance, this is what the signal looks like. And so what's really critical is this charging curve could be high enough that the current is high enough, it could damage the I/O pin of the Arduino or whatever you're driving. But the critical thing here is that this does not just go from 0 to 5 volts and the MOSFET turns on. There's this whole thing that happens. Now, I'm going to step outside of my comfort zone. I'm not 100% sure, but I'm almost positive that this effect that we see here is called the Miller plateau. And this is really bad because this is where the MOSFET is sort of turning on and off, and this could actually cause it to overheat. Now, if you're just turning on the MOSFET once per second, like we're doing here, this isn't going to be a big deal because it has a pretty high duty cycle, so it's able to recover itself. However, this is not a good thing. You don't want the MOSFET to do this. You want a nice, clean turn on. So this is cool. This is exactly what I was hoping to see, is that the MOSFET is not just turning itself, oh, that's not the right button at all. The MOSFET is not just turning on like straight up, okay? So what we're gonna do now is, let me stop the scope, and then we're going to, you can't see it. Oh, yeah, there it is. I'm gonna hit reference, and let's copy channel 1 into the reference, because now what I wanna do is disconnect the Arduino, turn off my power supply, and turn off the load, because what we're going to do is we're going to hook up another board now. Okay, so this was the 0 ohm resistor. So it's just like if we didn't put a gate resistor on our MOSFET. We saved the waveform so that we can see what it looks like. Let's see, Geek Boy, more so with a fast enough sample rate that will trigger 2x interrupts. Oh, since it flips between the levels, if that's like an input. Well, this is, yeah, if this was like the input, what we'll look at next, what I want to look at next, and I want to make this point, but the next thing I want to look at is what the drain source voltage of the MOSFET is, and then maybe we can look at both the gate and the drain source at the same time. But I want to compare, first I want to compare what happens when we hook up, so we got to do the same thing I did before. So I need a couple of header pins. Because I do want to, how are we going to, okay. I'm going to kind of hack this together because I realized, since I realized we're missing, oh, I know, nope, because that's not hooked up to Greek. Now I wish I put header pins on this board. On this board instead we left the header pins blank, which is a bummer. It's going to be a bummer for a couple reasons, but we'll survive. Okay, and then throw this guy in here, and it falls out immediately. That is perfect. That's totally what we want it. So MOSFET is more sensitive to varying voltage than a BJT. No. That's not what I'm saying. What I'm saying is a MOSFET is not a pure voltage device. Just like a BJT is not a pure current device, but for completely different reasons. What I'm trying to say is that the gate of the MOSFET does have a current effect associated with it. Now, that current effect is not having a direct effect to the output, the channel between the drain and source. It's the current itself is not what's causing the drain and source to change. It's the fact that it's the capacitance of the gate. And so we're observing that behavior by looking at the current, so to speak. Okay. Arduino will go to, let's go gate signal and then ground. And then ground. And this is where I was just realizing, this is going to be kind of tough. That's not going to work. What could we do? What could we do? I'm going to just hook this directly onto the MOSFET, making sure not to short it to the source. And then that should allow us to connect this into here. That's not going to work. Let's change this out with a male-to-male. And then I can just, we'll just kind of force it in to work for this purpose. I hope I didn't need that for something. Let's put this into here. All right, so we're still going power supply to load. Load comes into the drain. So we're doing the low side switch, and then source connects to ground on the Arduino, and it connects to negative on the power supply. Those are connected together, so that should work. So let's turn our load back on, power supply back on, and then Arduino back on. And we're switching just like we were before. Beautiful. Okay, so now we want to switch from, let me do this guy. So now we'll plug our scope back into what we were measuring before. Turn it back on. Yeah, that's what I wanted to see. Oh, yes. Yes. Okay. So check this out. I need to try and get my... Okay, let me turn the reference off and then we'll come back to that in just a second. So on this board, on this test board, we have a gate resistor of 2K. So just to point this out one more time, so that we can see it in schematic form, what I'm talking about is I have the gate signal coming from the Arduino is right here. That goes through a current limiting resistor, which then goes to the gate of the MOSFET. Previously, I had a 0 ohm resistor. So that was basically like saying that there was no resistor between the Arduino and the gate. Now I have this, I think it's either 2 or 3K, I can't remember what it actually is. But now we have a resistance between the gate and the MOSFET. And what I wanted to point out is, look at what happens to what? Then what was I looking at? Oh. So look at our signal. We come in, we go very clean, 0 to 1. There's a little bit of ringing. This ringing is probably the inductive effects of maybe these, the inductive effects of the jumper cables that we're using. But it's nice and clean compared to what we saw before, right? Now, what I need to figure out is how do I get, because I moved the, oh, I guess I could just move the, if I move the trigger reference, okay, we'll do this. This is not how I want it to show the measurement, but fine, whatever. Because what I want to do is I want to move whatever. So this is what now this is what we've got going on. With no resistor, notice how the MOSFET, it rings a little bit, but then it does this plateau and then it charges up. And so the gate the gate capacitor is causing us all kinds of problems. However, with a series resistor, we get a nice, clean, sharp turn on. And that is very, very critical. So I think the next measurement we'll try to look at, and I got to think about how we're going to hook it up, is I want to show the voltage across the MOSFET while the gate is turning on. So I got to think about how we're going to do that with the probes that I have. But this was actually the thing that I wanted to show. In fact, let me grab a screenshot of this before I forget. I think I broke my USB drive right before the stream started. No, it looks like it saved. Cool. So this is the thing that I wanted to show, was with no gate resistance, we get this really strange effect. And I need to do a better job of explaining what's going on here, but I also need to do a little bit of homework to make sure I fully understand it myself. But I believe this is basically, the MOSFET is not fully turning on, and that's bad. It's going to cause a lot of resistive heating. Up here is, this is the ideal way we want to turn a MOSFET on, where we actually turn it on nice, sharp, quick. It just turns on. Yeah, screenshots just in case. Yeah. I have such a bad habit of getting the measurement I want, and then I go back to my desk, I write the script, then I come back to the scope and try to replicate it, and I can't. And it's like, especially when it's just like, oh, I just wanted to show this real quick, then I have to spend an hour trying to remember what I did because I forgot to take a screenshot. Okay. Cool. Now what I want to do is I want to look at the gate and I want to look at the drain and source. The problem is it's going to be difficult because of how I have this set up, but I think we can do it. So what we're going to do, just to be safe, let's turn everything off. Let's turn off, disconnect the Arduino. Let's disconnect the Arduino, turn off power supply, disable the load, because we're going to use the differential probe over here, which means I need, this is where I wish I had put header pins on this board instead of just leaving the solder pads. So what we're going to do is we can put away the square pin. Wait, this is my single ended probe. So I'm going to put away literally yesterday I was just doing something with driving MOSFET incorrectly. Cool. Yeah, now this is something I've wanted to do for a very long time, and being able to, since I started doing live streams on a regular basis now, this was just on my project list of make this board. It didn't, like I said at the very beginning, if you weren't here, I did make a couple of mistakes, or at least one mistake. I overestimated or underestimated the current sense resistor, so we can't do the exact measurement that I wanted. But that's okay. We're getting close to, we're still getting a good set of measurements from this, so I'm okay with that. All right, so we're going to hook that up here in just a second. And then I need my other accessories because, and I've never used these before, so this will be fun. We're going to hook up, does this go a specific way, I wonder? I can't go that way because this is supposed to be positive. Okay, so now I should be able to handhold my differential probe, but I'm going to want to hold it the other way. All right, and then just for reference sake, let's do, let's disconnect, let's put this one, the differential probe over here, and put this probe over here. And then I'm going to turn my reference off. We'll probably want channel 3 to be 1 volt per division, because I think that's what it was before. So channel 1, we're going to plug now into where the gate used to be. Okay, and then let's add a label. Let's see if I might be able to do this faster with my mouse. I wanted to add a label, and the label is going to be gate. I'm pretty sure this is already in here. Maybe not. I thought they had VGS and okay. So we'll just do what is this? This is going to be this is gate. Enter. And if we go to channel 3, are we on channel 3 now? And then we'll do same thing. And then this one's going to be caps VDS. Enter. And so it's kind of small, but we can see the orange trace VDS. I don't want to go that far. But at least there is a label on the screen, even if it's a little bit difficult. Solder some pins on for now. 90 degree would be fine to stand. Yeah, I think I'm going to try to handhold it for this board. The other board has pins on it, so it'll be easier to make another measurement. But I don't want to take the time to solder again. So, okay, let's turn on our load. Connect this. Turn this on. So now we're getting our switching. So what we want to do first, okay, cool. So we're getting the gate signal. We're seeing that is switching. And let's try to give you guys at least a little idea of what I'm trying to do. And then I'm going to take this probe and we're going to touch it to drain and source. I'm going to hold it with my other hand. So back, which channel is active? Okay. Uh-oh. Why am I not getting anything from this one? What mode is this in? Is this in not in differential mode? Probe, common mode offset. I might need to dial that in. Because it does have a 12 volt offset. Okay, let's do this. It's saying it's clipping. Yeah, I got that. Why isn't it letting me see? Uh-oh. I did think of something. Let me turn this voltage down. Ooh. Nope, we're gonna need at least 7. Is 7 enough? Okay, 7's enough to get something going. Did I hold this backwards? But it's differential, so it wouldn't have mattered. So now my common mode is 7 volts. Huh. Nope, that's not what I want it to do. Interesting. Okay. Okay, okay. Now I see what's going on. Let's get a little bit more common mode offset. I shouldn't have that much of an offset though. All right, bummer. That's not going to do what I wanted it to do. So if we look at we just go single-ended. This might get me close to what I was hoping to see. Nope. Bummer. Yeah, the probe's not working the way I thought it was going to, and so it's giving me a little bit of trouble. I thought we would be able to, if I dial in 0 here, what happens? Okay, so that's not actually offsetting anything. And it's only letting me do a 7-volt offset, or a 5-volt offset. I thought this had a wider offset range, and so I thought we would be able to capture the VDS voltage directly. So since we're not able to see exactly what I wanted, I'm not too worried because we're at least, I want to, let's at least compare this. So it's at least letting us see, let me stop the scope so I can talk while I do this. So it's at least letting us see the yellow trace is still the gate. We're still doing the 2K resistance. And we can see that the drain, the drain of the MOSFET, so this is drain to ground, it kind of blips a little bit. I wonder if I should just swap the probes and make a single-ended measurement that way. Yeah, I'm trying to monitor VDS, and so I was trying to use a differential probe across drain and source. The problem is, and I didn't think about this, is the common mode of that drain source is whatever the DC measurement is, or whatever the DC, whatever the supply voltage is. And so I thought we had 10 volts of offset available in this probe, but it looks like we can only do 5 volt, which is a bummer. I don't think we can AC couple while we're using the probe. Nope. Darn it. Ironically, I do have a probe that can do it, but we're not going to take the time to hook that up. So what we could do is swap the probes. I could put the differential probe on the gate, because then we can at least see the gate signal. And then I can use, because then the single-ended probe will be able to get a much better look at what VDS looks like, because we should be seeing VDS go so we've got 12 volts to a load to VDS, so it'll either be when we turn the MOSFET off, it'll be at source voltage, or the supply voltage. When we turn it on, we'll get a voltage drop. We should be seeing practically 0, and we're not. That bothers me. let's just try real quick what the single-ended probe, see what the single-ended probe sees. Where did I put the case for that one? Because I want to know if I want to know why is the differential probe, is its common mode rejection just having trouble? Why isn't it seeing why isn't it seeing? Because its differential range is supposed, I'll have to go back and look. It must not have the same range. It must not have the range that I thought it did, because it's just not working the way I expect it. So let's go to this probe real quick. So this is a single-ended probe, which is like a traditional scope probe. The difference between like this and a passive probe is this is what we call an active probe. So it has very low capacitive loading and very high bandwidth. Whereas a passive probe might look like a 10 picofarad 10 picofarad capacitor. An active probe like this will look more like a 1 picofarad, or I think this is actually even less. It's 800 femtofarads of loading. So when we have like the ringing in the signal, this probe is more likely to reproduce it correctly versus a traditional passive probe, which you normally would use with a scope. This probe is differential, and so it's actually just like the op-amp circuit we were building a couple of days ago. It takes the plus and minus, subtracts it, and then shows us the difference on the scope screen. However, just like an op-amp, it has a common mode input range associated with it, and I thought we were within its range, but I'm starting to think we are not. So what I'm going to do now is, I know that it can at least measure the gate signal correctly, so we'll use the differential probe to measure our gate, and then I'll use the single-ended probe to look at the drain to ground voltage, which is effectively the same thing as drain to source. So we'll plug this one on, make sure that it's not quite going. Oh, I put that in backwards. So let's get the scope going again. Let's go ahead and bump this back up because I want to make sure this MOSFET is turning on. And then go to channel 1. Take it out of normal so we can see what's going on. Did I hook it up correctly? Yeah, gate to ground. Oh. I didn't move the probes. So channel 3 is now our gate. And then where's my trigger signal at? Now we go back to normal. Okay, so now we're seeing our nice clean gate signal. And now I can poke this onto the drain and source. I'm sorry, drain and ground, which is effectively source. Now I'll go back to channel 1. Let's find that one. Where did it go? Interesting. Huh. Well, once again, that's not what I expected. We should be seeing Okay, so the orange trace is our gate signal. The yellow trace is our drain signal. And I was expecting, am I not thinking this through correctly? No, because there should be a voltage drop across the load of 12 volts, causing the voltage drop of the drain to source to be practically 0 whenever the gate is on. So then why are we measuring? Why is that staying on almost all the time? I'm going to turn on a cursor, and I want to put it on the yellow trace, and the yellow trace, the cursor's at 12 volts. Yeah, but drain to source should go to 0 volts when the load turns on, and it's not. That is so weird. That is so weird. Okay. I don't fully understand what we're seeing. And wait a minute. Oh my God, really? Oh, okay. Well, that explains that. Oh goodness. I was like, I knew this had to be wrong. There we go. Okay. There we go. There we go. That, yeah. That's what we wanted. Okay, let me stop that. I'm gonna just turn this off. Just to quiet it down. Okay. Yep. So, okay. I mean, part of this, now, one thing I do want to mention, and I guess I could probe the same point, blah, 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 but I'm not sure what the propagation delay between the two different probes is, so things aren't going to line up exactly in time. There's going to be a little bit of skew just because the two probes have a different prop delay. But I'm not too worried about that. What I wanted to instead look at, so here's our gate signal. It turns on nice and clean like we talked about in the previous section. And then here's our drain voltage, and we can see it's 12 volts. The gate turns on, and I do think this might actually be the delay of the load, but I'm not positive. So the load turns on, and so the load starts to draw current, and then I think this ringing is actually the load itself because it's an electronic load. They're basically highly reactive, even though they're supposed to be pure resistors, they're not. But basically what we see is the load is 12 volts, it turns on, rings out a little bit, and then it stays on. That's exactly what we wanted to see. Let's take a screenshot of that. Let me mark that. Okay, so now what we're going to do is we're going to move everything over to the board without a gate resistor. This was actually, I changed my mind. I do want to at least add this. 2K resistor. Screenshot this. Okay, and then let's delete that annotation. Which I can't remember how to do now. Let's just clear. Okay, so now let's switch over to the board that has no gate resistor and see what happens. That should be fun. Okay, disconnect our Arduino. That's pretty cool though, right? I mean, come on. Isn't it cool that we can see the gate turn on, we see the MOSFET turn off? I think that's pretty cool. I just wish we had a good, we could have put a current sense resistor, darn it. We should have put a current sense resistor on the drain so that we could measure the current going through it. Okay, revision 2. All right, let's go to this. I'll let you guys look at that. Yeah, maybe this time, well, we're going to do the exact same measurement, and then I want to back up one step and see if we can calculate or measure the skew between the two probes, but let's just do one thing at a time. All right, we'll leave that one in there because that's fine. No, we're going to do the same. We're going to hook this up the same way now that I realize the mistake I made earlier. Yeah, actually, I think, Kempton, I'm not entirely sure what you meant, but I think being able to see the fact that there's a delay between the time the gate turns on and the transistor turns on is pretty cool. Like I said, though, we have to be careful. That could be the electronic load. What I would say, what we might try doing, when we can't, I mean, we can do this, is maybe we should actually try using a, we should try using a, I've got some resistors. While they're still somewhat inductive, at least they're going to be a little less reactive than what's in the load. But I've got like these huge power resistors that we could use. So let's go here and here. Nope. Okay, I'm going to make this mistake later on, so I want to fix this now. I don't know why I made the red wire the ground wire. That's just asking for trouble. Okay, so source is connected, drain is connected. This needs to go to the ground on the Arduino. And then we're going to connect our probe into, well, this may not be the exact same measurement then. We're going to try. We'll do that, and then I can hook up. Oh, I know what I did last time. Let's try and hold to the same thing we did, which is going to be difficult because my pin connections are totally different. How am I going to get this and that connected? I don't think I'm going to be able to. So what if we did, I'm going to sacrifice one of my ground pins for the sake of a measurement. The problem is when I built these boards up the other day, I didn't do the header pins the exact same way, and now I'm wishing I had, because it's I can't get to the signal I need to get to, because I thought, I don't think this is going to work. Okay. I don't want to change anything though, so what can we do? One option is I could just desolder that pin real quick and set it up the same way we had it. So let's just do that. Because I really want to get this, I really want to make the same measurement we just made. And I feel like if I do this, if I change too much, then it won't be an apples for apples comparison. So let's just remove this pin and set up this board the same way the other board was set up. Let's see. I have the most technical question ever for you. Well, I highly doubt that. If my day job has done anything, it's prepared me for highly technical questions. Not that I can always answer them, but at least I've been asked them before. So what I was trying to say is, what we're going to do is, over here on this version of the board that has the 0 ohm resistor, I put these header pins, and turns out I don't think we're going to be able to use the probes the way I thought. So what I want to do is, just like on the other board, I'm just going to remove the pins so that we have blank solder points, so that I can just touch the probe down onto it. Did I ever consider other facets? I'm not answering the other question. I don't really think that's appropriate for the chat right now. And if you had asked the question in a mature manner, then I might have answered it. So did I ever consider other engineering disciplines? Not really. When I was 12, I got introduced to electronics, and I just really enjoyed it. and I basically knew at that point I wanted to go into electronics. In retrospect, I sometimes wish I might have gone the mechanical engineering route, and the reason for that is just because I think, sometimes people can learn things either naturally or with a lot of effort. And a lot of what I've learned in electronics, I won't say has taken little effort, but it's more or less come naturally. It feels like it's come more naturally to me. There's a lot of things I've been able to figure out on my own and then reinforce it with proper training and facts. Whereas with mechanical engineering, I get really stuck on a lot of concepts that I wish I had formal training on. Now, as I say that, it could just be because I went to school for electronics or electrical engineering. That's why it comes easy. So that could be the case. But sometimes I wonder if I should have gone mechanical and then minored, so to speak, with electronics. I mean, I think more importantly, if you have an engineering mindset, that doing anything engineering related that's the more important aspect, because to me, engineering is how do you make trade-offs, how do you learn, how do you solve problems. And so any engineering discipline is going to teach you those basic concepts. And so, I don't think there's a right or wrong for engineering. I think it really comes down to just what are you suited for. I don't even like to make fun of or make jokes about, oh, well, you're a civil engineer, ha ha ha. It's like that kind of stuff just never, like when my classmates and such would do that, I just never kind of got that, because it's like, it's still an engineering discipline and it's an important one. Let's do that, and then just add one more solder. Now, related to learning electronics, where did I learn to solder? Well, clearly nowhere, because I just took out part of that screw terminal. As I said on one of the soldering videos, I'm pretty terrible at soldering, actually. Okay, cool. We got what we wanted. Now we're good to go. Cool. Now let's get this hooked back up. Ground to, this is going to go, this was for the gate signals, so we can hook that up. Let's turn this off. And then I can plug the load back in. I was going to say, man, it is so quiet all of a sudden, and it's because I turned that load off. One of these days, we might actually do a stream where I fix or replace the fan in there with like a Noctura or something, because it is just too loud. All right, let's go. This will go to our source. And then we'll hook this into here. All right, that's all connected up. Now I need to get the load going again, so I need to reuse my power cable. Turn that on so we get noisy again. Turn on our voltage and get the Arduino going. Oh, so now we can hook up our probes. So let's get this probe back in. And let's take a look at what's going on here. All right, on the scope screen, we can see our gate signal. What? Well, that doesn't look anything like what we saw before. Did I hook up the wrong board? Or are we just in a bad scale? Yep, okay. Let's do this. And then we're going to take this guy and go over here. Okay. Now, isn't that interesting? Huh. That's the exact opposite of what I expected to see. Okay. This time we don't see any of the ringing we saw before on the load, even though the gate is doing all this crazy stuff. It does, there is, so when this ring occurs, we can definitely see there's an inductive spike on the output, so that's bad. But it is interesting how this turns on faster. And so I wonder if because we were so zoomed out, if we didn't actually see the relationship between the gate time going on and this. But yeah, that's interesting. Is this some type of FET driver? Yeah, it's literally a FET driver. So what we're doing is we're using an Arduino to drive a MOSFET. We've got two different test boards, one with a 0 ohm gate resistor and the other with a 2K gate resistor. And what we were talking about before is how we see this turn on effect of the MOSFET. And then, so this is the orange is the gate, and then the yellow is, in fact, why I'm thinking about this, because this is going to confuse me later, is we need to turn that label off. Yeah, so yellow is, or orange is the gate, and yellow is VDS, effectively. Not what I was expecting to see. Not at all. Okay, let's do this time. Let's go into our ref menu. And reference 1 we'll copy from channel 1. And reference 3 we'll copy from channel 3. And then I thought I could do, let's do red. No, I want red. And then we're going to turn it off. And then reference 1, we'll do this as not label. Why did I go to label? Let's go to color and make this one, I don't know, light blue. That's fine. Okay, and we'll turn that one off. Now, I know this is tedious. Now I'm going to go back to the other board because we're on a different time scale, and I want to see if that messed us up. So we'll take this and plug this into here. Probe will get plugged in there in just a second. Wait a minute. I just realized something. I think I forgot to turn the load on. No, it was clicking, so it was on. I'm going to do this, throw this over here. One, two, three, presto changeo. Okay, quick check, that looks good. This will go here. Should be able to turn this back on. Plug this back in. Okay, he's clicking away. Plug the probe back in and then run the scope. Interesting. Wow. Huh. Well, I'm going to have to do some homework because this is not working how I expect it. Source sink current problem, maybe. Could be. I think frankly, I think what's going on is I'm not understanding how the MOSFET turn-on behavior is working, because it's actually sort of done the opposite of what I expected. How can we, if we move this over to maybe here, because if I go turn my references back on, yeah, open up the window. R3, turn that on. And then if I move these around, it's not tied. Okay, that's just more confusing than helpful. Okay. I want to look at, so this is, I don't care about the drain voltage at the moment. I just want to look at the gate. If we zoom in on this, what I'd like to know is, let's go measure on channel, nope, that's fine. On channel 3, what is the rise time? So 2.8 nanoseconds, okay. Okay. What test instrument oscilloscope are you using? It's a Roden & Schwartz RTM 3000. Okay. Well, this is quite fascinating because this was totally not what I expected, and I don't have a good explanation. Which means I have some homework to do because this is not doing what I expected, and I don't know why. And it's starting to make me think I might have had some misconceptions, because, in fact, I almost thought this was going to work the opposite of what we're seeing. Interesting. So what I will do is I will post the schematic, let's see, I'll post the schematic and the 2 screenshots on the Discord. So if you go to AddOhms.com/Discord, then you'll get redirected to the Discord server. I need to reread how MOSFET turn-ons work, because this is not what I expected. I mean, there's 2 things that are bothering me. Is we see this delay, and this delay is not, I don't expect that. I can't explain it, because not only do we get this, we don't get this delay when we don't have the resistor. I would have expected a sharper turn on to cause this to turn on faster. But that Miller plateau on the other, because we're not even getting a Miller plateau here. Or is that applied? Oh, now I gotta wait. Okay, all right, I've got some homework to do. So yeah, KAO Pro, yeah. That was sort of when I decided to start, so since I'm not traveling as much as I was before, I decided to start trying to do at least 2 live streams during the week and 1 on the weekends, which next week is going to be that case. I think I'm only going to do Wednesday, Friday, and Sunday. And one of the reasons I wanted to do live streams is because it's really hard to get this kind of thought process or why is this bothering me into a video, because usually when I do an edited video, I've figured out what the problem was and then I sort of backtrack from there. And I think it's helpful for people to see, what are the things that I see I don't understand, or I'm saying from my perspective, if you're watching another electronics streamer, same thing would apply with them, is, you sort of get to see, okay, what about this actually bothers me? And what's happened here is I had a very strong assumption about what to expect when we looked at the scope screen. And we are not seeing what I expected. I almost want to say we're seeing the opposite of what I expected. And so now I need to go and do a little bit of research and look back through all my notes and try to understand, what am I missing here? And frankly, what happens sometimes, seriously, what'll happen is after I stop streaming, I'll go eat lunch. While I'm eating lunch, I'll go, oh my gosh, that's what was going on. And I just didn't see it because I'm on stream. But I also like to let you guys try to think about, okay, what could also be going on? Sometimes there's people in the chat that know more than I do, which I shouldn't say sometimes, it's probably more than sometimes, probably most times. And so it's always helpful for me because we can say, okay, well, try this, try that. But this one just kind of got me. I didn't expect these two different types of results. So just to help those that are coming in or might have missed this one more time, we've got this demo board that we built. It's got a MOSFET on it, and then it's got a shunt resistor. This shunt resistor right now is like 40 milliohms, so it's not contributing a whole lot to the circuit. There's pads for pull-up and pull-down resistors, which are not populated. There's also a pad for a capacitor, which is not populated. In fact, one of the experiments I want to do is add a capacitor, slow the rise time down, and see what happens to the turn on. And then we have a current limiting resistor. On this board, it's populated with it's either a 2 or 3 kilo ohm resistor. I don't remember now. And then on the other board we were looking at, we actually have a 0 ohm resistor. And the intention was to try to show what happens when you do or don't have a series resistor on the gate of a MOSFET. Ultimately, what I wanted to do was show that there is current flowing on the gate by measuring across the shunt resistor, but I need to get a bigger shunt so that we can actually get enough voltage so the scope can see it. Wait a minute. Hold on. All that said, that's being driven by an Arduino. What's the MOSFET? MOSFET's it's the logic level one that everybody likes to use. FQP60N30L. I have a thought about what might be giving us grief. I want to make one change and see what happens. I want to disable the LED on the gate. I just thought of this. I just thought of something. So we'll make one more. Well, that was weird. I don't know why that happened. I'm going to make one more measurement here. So let's go to, I'll leave this up if people want to look at that. So when we designed so I put a little gate a gate LED on the board, and that was just kind of well, all projects should have an LED kind of thing. But I want to so it has a solder point that we can use to disable it. So I want to disable it. So this is 350. Done. Let's get right onto this enable pin. Okay, so that should be disabled. And just in case I want to go and make a measurement over here, let's disable this one as well. Okay, turn this off. And I think I did hit one of these jackets, didn't I? Okay, so let's get this probe. We'll plug back in. And then we will turn this off and turn the noisemaker back on. Maybe in the future, I'll make sure I have enough cables for everything. Gotta love solder bridges. Yes, I agree. I was so glad we did that, because otherwise this would have been a lot less fun to figure out. All right. Oh, no. Really? Oh. Oh. Okay. Okay. Oh. Let's see what this looks like. Okay. So we cleaned up the ringing by removing the LED that was on this circuit. Not positive why that's an issue, but gosh, when we're gonna go back to the board. I think I know what was going on. So let me save this, stop, take a screenshot of that. We're gonna switch over to the other board and see if our measurements are different now. And if they are, then I'm going to hypothesize what I did wrong. You know, the funny thing is, I really thought this was going to take like 10 minutes and then we're going to get to some RF stuff. So that's definitely going to have to happen later this week, because I've got all these low noise amplifiers that I want to play with, and I think it'll be fun to do that on stream. I'm going to pull out a software-defined radio. I've got two that can transmit, so we'll use those to... Yeah, so we'll use those to kind of play around with some stuff. And then I want to compare to my Nano VNA and blah, blah, blah. I've talked about that plenty of times. Okay. Okay. So we're going to turn this back on. Turn on our power supply. Run the scope. Okay. So we are still seeing, this is good. So the gate is still kind of doing its funky thing. Okay. And then if we go and look at this, okay. This is a little more believable to me. Yeah, this is much closer to what I was expecting. Why can't I control channel 1? Oh, because an active probe, that's the most I can get out of it. Okay. Yeah, we're right at the limits of the probe. Oh, I forgot to stop it. Okay. So first shot I want to get, I'm going to get a couple screenshots and then I'll talk, sorry. So we're currently looking at the board that has no gate resistor, or 0 ohms for the gate resistor. All right, and then oh, was it just the way I was holding the probe? Okay. Okay, so it's still not quite doing what I expected, but at least now I verified something. Let's stop it. Yeah, so what I realized was, I think one of the measurements we made, the load wasn't actually enabled, because I thought it would only make the relay clicking noise. Can we see too? Yeah, I guess so. That'd be nice, wouldn't it? Do you have a load across drain and source? There is a load between the positive supply and the drain, which is an electronic load set to 100 ohms, I think. Yeah, so we basically saw the same thing we did before. I thought what happened is I forgot to turn the load on because I'm not sure if you guys can hear the clicking, but whenever the Arduino turns on the relay, turns on the MOSFET, I can hear the relay in the load switch, and so it sounds like it switches even if I disable the load. So I thought maybe I had made a measurement without the load enabled, but that's not the case. But yeah, this is still doing the same thing we saw before, where when we get to about half the threshold, it turns on right away, nice and clean. What you might have missed, because I forgot to switch the input over, is I'll show you the last. We'll look at the two screenshots side by side. See if I can manage this. There's a problem with the drive. No, there's not. So is it this one or this one? Yeah, okay. So previously we saw a bunch of ringing, and I think that was just a measurement problem. I don't think I had the ground on there as well as I thought I did. And so here's what we see the difference is on the right. Let's see if we move this over to about there. And then we can look at this one. Keep looking over there. So here we can see, this is the one on the screenshot on the right is 0 ohms. The gate turns on, it does this level thing, it rings a little bit, and then it charges up. So that's where we see the load get turned on very quickly, very sharply. On the left, we have with a 2K gate resistor, the gate turns on relatively fast. It rings just a little bit, but it turns on. No need to really zoom in on that. Nothing too exciting there. I measured it one time. It was like a 2.8 nanosecond rise time. But what we notice here is the load takes a little bit of time before it turns on, and then it does so kind of slow. And frankly, I wasn't expecting that. I thought this was going to be the opposite response. So, but at least now I've got two good measurements that we can go and research and understand better what's going on. So, yeah. If you're using the logic level MOSFET, I would think the turn on turn off would be more an internal thing as opposed to a MOSFET with logic level input. Michael, I'm not entirely sure I follow what you just said. The turn on off would be more an internal thing. I don't know what you mean by the internal thing. I mean, the thing is, there's actually no such thing as logic level input MOSFETs. That's sort of a phrase that got made up. They just refer to MOSFETs that have a very low VGS threshold. No MOSFET has a logic level where it turns on. They're all VGS. It's all based on the VGS threshold. It's just that MOSFETs like the one we're using, the FQP 60N30L, which, yes, I know, I've even called it a logic level MOSFET. All that phrase means is the VGS level is low enough that a 3 or 5 volt signal can turn it on. But it's not like there's some kind of signal conditioning that happens in front of the gate. It's still just a regular MOSFET, just with the low VGS. And so one other thing, we're not going to do it today because I'm running out of energy, is the other thing we could try. Since you bring up the logic level aspect, One thing we could try is we could use the arbitrary generator to generate, I think I can do up to a 10 volt signal. 10 volts tends to be a much better voltage to drive a MOSFET. And so maybe as a follow-on experiment, I can set up the generator so that we can get like some 0 to 5, 0 to 7, 0 to 10 volt. And then maybe I could even look at trying to adjust what the rise times look like to see how those affect what we're doing, which is effectively what the current limiting resistor would do, is change the rise time. But where I'm at is, and I've said this before, I just got to say it again. These are not the results I expected. I thought we were going to get something different. And so now I need to understand why we got this. Man, I sort of want to do the... I really want to do a... Wait a minute. Okay. So I am ground referenced. Yep. I was thinking I was thinking I had something floating, but I don't. Because what we could, I mean, it wouldn't take that much. Oh. It wouldn't take that much to set the generator up to do exactly this. If we did a pulse, what's the max amplitude? We can do 10 volts peak to peak, but I don't think I can do, can I do a 5 volt offset? And then let's do save setup. This is going to be FET Live. Save. Want to see what I can get my built-in generator to output, because that's going to change what I want to do next. So I've plugged it into channel 2. We're going to the generator. I did a default setup, so I got to redo the setup. So I want to go to pulse, and the amplitude, I'm going to set it to max. The offset, set it to the max. Turn this on, and then get a good trigger. What am I looking for? Move this down. So it looks like we're going from, yeah, so we're going 0 to 10. Okay, and then let's change the frequency to 1 hertz. Normal trigger so that we can actually see it. And then the next thing I want to know is if we measure channel 2, horizontal rise time. Okay, so it has a rise time that's faster than the Arduino. The Arduino was 2.8 nanoseconds. This is, wait, no, it's way slower. It's almost a millisecond. Okay. I can do math, I swear. Oh, that's because that's what the edge rate is set to. Oh, that's the minimum. If I had a Schmidt trigger, we could do this. I have a feeling this is going to be too slow. So, well, it's already outputting, so why don't we do something with it? Okay. I need, it's usually connected to my generator. I need a BNC to flying leads, which I think is not that one. It's not that one. What's this one? Is it this one? Or is this one broken? It's one of these. Neither of those. Oh, I just used them the other day. That's probably why I can't find it. Here it is. Okay. Oh, I can't wait to move and get lots of space so I can have plenty of room for all my cables. All right, so we're going to take our signal and we're going to go remove the Arduino. He's out of the picture now. But I don't want to ground this through the scope. So we're going to hook this up, turn this off, hook this one up, move these over, take this one out. What I'm worried about is that needs to be connected to ground. So I can connect that to ground this way. So what I've done is my oscilloscope has a built-in function generator, which is what we were just looking at on the screen. And so I'm going to use that to generate a 10-volt signal to turn on the gate. And so by doing that, I want to see how this responds relative to what we were just looking at. And then okay, so that should be grounded. Okay, so now if that's on, if I turn this on, nothing should be happening. If I turn on the output, it's turning on for a short period of time. Let's change the duty cycle to 50%. It's going a little faster than it was before, but that's okay. Now on the scope, what I want to look at is we need to go and do re-setup load. And it was the setup. Oh, where did it go? What did I call it? It was like live. Can we do file view? I don't want icons. It was FET live or live FET. I forgot to hit save. Okay. That's what happened. All right, so let's go ahead and go to generator. Now I got to set that back up because I wasn't thinking when I did that. Go back to pulse. We're going to do frequency of a hertz, an amplitude of 10, an offset of 5, a duty cycle of 50. Turn that on. Duty cycle of 50. Okay, and then channel 3 is our gate signal. So now we'll change our trigger to be channel 3. Kind of move it up here, do like 1 volt, go into normal because we're slowly triggering. So of course it's going to be kind of slow to see what's going on. Oh, okay. Now we're overdriving the probe. That'll be fine, I hope. And then we want to look at channel 1 and see what it's doing. Interesting. Okay. Okay. Yeah. Yeah, C++ RAID. Oh yeah? Are people coming in from somebody else? Ah, T-Sodding. How you doing, man? Yeah, so we've actually been looking at how to measure, we've been looking at some MOSFET measurements that aren't quite doing what I expected. So if you're not familiar, MOSFETs are a transistor. It's a type of switch. And the switch, or what I wanted to do is build a board, which is what we're looking at here, that allows us to make measurements on the MOSFET. And so to give you some context, this is the schematic of what we designed. Here's our MOSFET. There's a current limiting resistor, which I wanted to show what happens when you have one of these and when you don't. The problem is the measurements we got did not match what I expected at all. And so we've been looking at trying to understand what's actually going on in the circuit. So my name is James. I'm the Bald Engineer. I have a YouTube channel called AddOhms. I also host a show on Element 14 Presents on YouTube called Workbench Wednesdays. I have a blog at baldengineer.com. And as you can kind of tell, I do lots of electronics related stuff. So like I said, in this case, we're actually trying to measure the parameters of a MOSFET and determine the question that's been coming up in a lot of my a lot of forums is, should you have a gate resistor or not? So where I'm at right now is the MOSFET is doing what I expect, but not when I expect it to. And I'm trying to figure out why that is the case. The last measurement we did was I took, this orange trace is the gate signal, and it's being generated by an arbitrary waveform generator. And then the yellow trace is the MOSFET turning on. And I've got it hooked up to what we call an electronic load, which is basically a programmable resistor, so that we can kind of control whatever the MOSFET sees. And what's interesting is, which board is this? Yeah, this is the 0 ohm. So what's interesting is the behavior is not at all what I expected. So let me see if I can try to explain. Could be PMOS versus NMOS. No, it's not a transistor technology issue. What I've got going on is this is an N-channel MOSFET, and it's configured as a low side switch, which means the source is connected to ground, and then the load connects between the positive supply and the drain. So we've got that hooked up correctly. Should be using an N-channel. Here's what's strange to me is with a 0 ohm resistor, so no gate resistance, driving from 0 to 5 volts, this is what happens with the gate signal. And I actually expected to see something along these lines, because what's happening is when the Arduino, so this was driven by an Arduino, when the signal turns on, the gate is actually like a capacitor. And so we have a little bit of inductive kick, and then the capacitor starts to charge up. What I didn't expect is that our load turns on almost right away. And so it turns on when the gate plateaus like this. I didn't expect that. Then what happened is I changed it to a separate board that has a that has a 2K resistor instead of a 0 ohm resistor. And so here we see the gate signal, it turns on, it rings a little bit, which we sort of expect anytime you have a high-speed signal. And even with this setup, we've got a little bit of extra inductance, so I sort of expect that. But what I didn't expect is there's this delay before the load turns on, or the channel on the MOSFET turns on, and I don't know why that is. I don't expect that. Voltmeters these days have web servers built in. Yeah, so this is an oscilloscope. And yeah, if you get an expensive enough voltmeter, they do have web servers built in. A lot of bench style multimeters or voltmeters that they're going to run in the $2,500 plus range. They almost all have a VNC server running on them. I mean, all instruments are just about any sufficiently advanced modern instrument is running an embedded OS anyway. And so most of them have gone to Linux at this point. And so getting a VNC server running on it isn't that big of a deal. Anywho, so now the last thing we did, and this is when you guys came in, is I've got a waveform generator that can go to 10 volts. 10 to 15 volts is generally the ideal range to turn on a MOSFET, even the ones we call logic level, like the one I'm using, because 5 volts is, for lack of better words, just enough to turn it on, but not all the way. Whereas 10 volts should really make sure that the channel is nice and wide and open. And so what's strange to me is it does turn on the FET nice and quick. Oh, you know what we could look at? I know it, I didn't zoom in. The problem is my generator doesn't ramp up very quick. And so it might just be a rise time or slew rate issue. Generator, turn the generator back on. What I want it to do is let's zoom in and see what the load signal is actually doing. Yeah, see, it's all kinds of crazy. There we go. I grab a screenshot of this. I'll get it from Twitch. Yeah, so see, this is a little more in line with what I expected, because our gate signal isn't very fast and it's kind of noisy. And so look at how this thing kind of starts to like wiggle around, and then it finally cascades or avalanche. I don't want to say avalanche. That's probably not a good idea. But yeah, so this thing kind of turns on, and I didn't expect that. So what do we do now? I guess at this point, I need to think about, why is this thing not doing what I expected? Yeah, because this is, hey guys, thanks for the follows. I appreciate everybody. Just to repeat one more time, so I do a lot of electronic stuff. Lately, we've been designing this MOSFET test board that we're using right now. And so the idea is it was just a jig to allow us to make some MOSFET measurements. And so right now, we're looking at what's called the gate signal, which in this case is the orange. And we're looking at the drain, which is effectively drain to source or drain to ground, because source is connected to ground, which is the yellow trace. And so we're trying to see, how does changing the gate resistance change the turn-on behavior of the MOSFET? And so far, I'm baffled to what's going on, because it's not doing what I expected. So yeah, it should turn on when you hit the threshold voltage, but that's also sort of one of these kind of details that gets overlooked. We simplify MOSFETs by saying that once you apply the threshold voltage, they turn on. And what we can actually see is we've got 3 different ways we've applied threshold voltages, and the MOSFET is turning on different with each one. And so we need to think about what that actually means for the FET when we want to use it, because it's not as simple as you apply a voltage and it turns on. We can see there are very different behaviors depending on how we apply that voltage. Somebody had asked, is the load dynamic somehow? The load is a little bit dynamic, so it's just an electronic load. While we think of them as programmable resistors, they're a little more complicated than that. So what I've got going on that you guys can't see is this is the load, and when it's active, we can see that it's clicking on and off because as the gate gets turned on, this load becomes active. And so it's basically, we can see that it's working like a programmable resistor. Right now it's programmed for constant resistance. Let me turn this off so that the screen stops updating. So right now it's set for a constant resistance of 100 ohms. So whatever voltage gets applied to it, it will adjust the current so that it acts like a 100 ohm resistor. And then next to it, I'm just using a bench power supply to provide the 12 volts. So it goes supply, load to the MOSFET board, and then blah, blah, blah. So that's what we got going on there. Kill that. So what type of transistor is it? It is a MOSFET in channel, and it is I had the data sheet open a minute ago. It is a FQP30N06L. I think I called it a 60L earlier. But yep, so that is that's what we're actually using. So let's see. Now, some people call this a logic level MOSFET, and as I was trying to explain to somebody else, that's a very common term that gets thrown around for this particular MOSFET as well as ones like it. But all that means is if we go look at its VGS threshold, it's between 1 and 2.5 volts. So in theory, even a 3.3 volt system like a Raspberry Pi has enough voltage that it can apply to the gate to turn it on. In practice, what we have to go look at are things like these graphs, the on region or the transfer or output characteristics of the MOSFET, because these tell us if we apply a certain VGS and there's a certain amount of current going through the drain, what will the voltage across that drain and source be? And what we can tell, and the only reason I'm showing you guys this, I don't want to get into the details, but different VGS voltages cause the drain source voltage to change. So even though you can apply as little as 3 volts to turn it on, the on resistance of the MOSFET is still relatively high, versus if you can turn it on with 10 volts, you get a much smaller on resistance. So more gate voltage is always better. We just call them logic level because 3 volts is enough to get them to work. If you go look at traditional MOSFETs, they don't even work until you apply 10 volts. And so that's where that whole thing comes from. All that to say is, I say all that because I just want to clarify that what we're doing, where we're using an Arduino to turn this on, it's normal and expected. It's just not responding the way I expected it to. So, okay. So that's what we got going on. And now I've got some things I need to go look into and try to understand why did these work the way they did. So, Okay, I have one last idea. Let me think through how we're going to do it. What we could do is replace the electronic load with a power resistor and see if our behavior changes. The problem is I don't have, so what is 100 ohms? So we have 100 ohms and 12 volts. So that's giving us 120 milliamps. So I squared R is a 1.4 watts. I don't have a 100 ohm resistor that has that'd be a 2 watt capability. If we did 12 volts and 1 ohms, that'd be 12 amps. Nope, can't do that either. Huh. Okay. I think, I don't know why that got, allow. I don't know why that message got caught in the chat. Yeah, I saw somewhere somebody made the comment that the MOSFET is the most man-made or human manufactured device on Earth. And frankly, it depends on how you count it, because what they're counting are MOSFETs or transistors inside of things like CPUs and chips. And so is that really the case? Okay, that's fair. But then what you really should be counting is the silicon oxide that's used for the insulation layer, because that same material is also used in other applications like in tires. And so silicon oxide is probably the most common man-made object, not the MOSFET itself, but that's okay. Resistors in parallel to increase the power handling. Yeah, I just don't have a good way to hook that up. One thing I don't want to do is I didn't want to use a bunch of resistors, because then the inductive elements get so high that it's going to cause more ringing and kind of taint our results. What I really need to do is find a power LED that will draw quite a bit of current, because then that would give us, I think that would give us a more realistic linear response versus a motor or a bunch of resistors, or wire wound resistors anyway. So I'm just trying to, well, nope, this is high side, so I can't do that. I was gonna say we could turn on yeah, one thing I was trying to avoid is changing the current too much. So what was the point? The point was to use something other than the load, which I don't think is an ideal load. I'm less worried about that at the moment. Now I think about this a little bit more. The fact that these screenshots are coming up so different really bothers me. Okay, that was a bad measurement. This was 0 ohm. This is 2K. And then, I haven't taken this screenshot yet. Okay, let me do this real quick, because I haven't taken screenshots of this last measurement, and so I want to make sure we capture that. So let's do this. I'm going to zoom this out. And then let's do a screenshot. That's good enough. And then I think I want to actually, let's try and zoom in, but I want to get basically what I want to do is just make sure I get a nice high resolution view of what's going on here. Okay, cool. All right. Yeah, I had labels on earlier, but orange is gate, yellow is VDS. same thing with these screenshots. Careful, because these screenshots, some of them do have labels and they're backwards because we had to move the probes around. So, okay. Okay, here's where I'm at. Like I said, I think I've got some homework to do. I want to go think about this. I'm going to also give some thought to the load issue. What I'd like to do is I still want to use the electronic load just because it allows us to program, give something programmable. But I'd also like to compare it to a real device just to see if we're getting a difference between those two. So I'm going to give some thought to that. As I mentioned earlier, if you want to head over to the AddOhms Discord, I'm going to post the schematic, even though you can download it from GitHub anyway, along with these screenshots. And I'll take a few minutes and label what each of the screenshots are. And so I'm going to post that into the AddOhms Discord. The way to get there is go to AddOhms, AddOhms.com/Discord. In fact, well, I think I can do it this way. Let me go ahead and just type this up real quick. So you have one half watt resistors. Yeah, so Michael, the resistor suggestion is probably one way to go. What I'm not liking about that though is when you put a whole bunch of resistors in parallel, then you end up with or a couple of resistors in parallel in series and everything. Especially through-hole resistors are going to have a ton of inductive effects, and so I don't want that to mess up what we're looking at. That's why I'm thinking instead, if I can find, like I think I've got some power LEDs that we could use, and then we could just do current limiting on we could just current limit them. So anyway, I want something that is not reactive, because my belief is the electronic load that we're using is very reactive. Same thing with flashlight light bulb. The only thing there is what its resistance is, but I like that idea. If I have a incandescent light bulb, then we could use that, and then we would just redo the measurements and have the load. I mean, that's still somewhat inductive, but those are mostly resistive. Yeah, so maybe we get a light bulb. I agree. I wonder if the load is affecting this turn on time. It's so weird that in this case there was a significant delay, but then in this case I wonder if that's about the same. Maybe it is actually about the same delay time, and this actually triggered it, and then it turns on. Huh. Oh man, I wish I had measured that. I just realized that if this was the threshold point where the FET turned on when this inductive spike occurred, then when this thing starts to drop, so from this drop time to this from this fall time to this rise time, so this is the gate, this is the drain. I wonder if that was, oh God, wrong button. I wonder if that's actually about the same time, and I just missed it because of the ringing. Because this is 0 ohm. Yeah. Oh my gosh. Why didn't I do that? Okay. Yeah. Okay. Incandescent bulbs change with resistance. Okay. Yeah, because the temperature as they heat up, they're Yeah. That's not going to work out too well. Okay. Tell you guys what. I want to go back. I want to remeasure these on the scope so that we can actually put the cursors and measure these time differences. And what I realized I should have done, and we'll do this, I should have saved the waveforms for both of these so that I didn't have to remake the measurements. So tell you what, let's give me a couple of minutes. I need to refill my tea. I want to grab a snack, and then we can come back and make more measurements. And so, yeah, I'll be back in just a couple of minutes. And while I'm gone, I'll turn the trivia on so you guys have something to play. And yeah, we'll do that. So I'll be back in just a couple of minutes. Okay. Much better. Very refreshed. I went and got some goldfishes. Oh, I should have got, I have candy covered almonds because it's Easter, and that reminds me of Easter, and I totally forgot about that until just now. So first thing we want to do is get the generator out of here because it's not helping. Well, it actually is helping quite a bit, but not for what I want to do. Because what I want to do at this point is redo the measurements we already did. I'm very sorry, excuse me. So let's get the Arduino hooked back in. And this is the ground. And this will be our gate signal. Hey everybody, thanks for the follows, appreciate those. By the way, if you have ideas for other trivia questions I could do, I would love to hear them. There's about 50 questions right now. And with the increase in streaming, oh, should have turned that off. With the increase in streaming, I'm starting to get through them a lot faster than I expected when I first wrote the trivia program. So if you got a favorite fun electronics fact, feel free to let me know. Probably the best way is over in the Discord, so AddOhms.com/Discord. Yeah, let's see. So Arduino is reconnected, and this is the 0 ohm. So I'm going to turn these labels back on, even though I really wish they were bigger because I don't feel like they're easy to read. So this is channel, I forgot what channel we were on. I think it was channel 3. So this was going to be gate. All right, and then channel 1, let's edit that label. And I'm just going to say drain, but this is really drain to source or drain to ground. But since source is connected to ground, basically the same thing for the purposes of this measurement. And the reason I don't really like these labels is if you look really close, you can see that they're down here. And then I am going to add this annotation, and this is going to be for 0 ohm. And that's the value of the gate resistor that we're currently looking at. So let's put that up here at the top. And then that way when we do screenshots, we will definitely be able to see what we're looking at. Okay, now we have load or supply to load, load to drain, and then source to ground, and source to here. All right, the Arduino is on. It is not on because I disconnected it to plug in the USB drive. So I need to find that cable. Let's get that. Plug that back in. So Arduino is going. We can turn the load on, and then we'll turn on our voltage. And I hear it clicking, so I know that it's turning the MOSFET is turning on and off. So now we'll run the scope, and what we want to get is channel 3 is our gate signal. Let's put it into auto so we can try to understand what's going on. So it looks like we need a trigger somewhere around here. So we'll go back into normal so we can try to get the transition. And it looks like we got a really slow time base. Or no, it's just taking a long time for the triggers to occur. So channel 3, move this up. Oh, wrong knob. Use the scope every day and I still get that wrong. Okay. So here is this is the gate of the 0 ohm resistor. And so the whole thing that's bothering me is we see this loopy loop, or this loopity loop. So we see this threshold. We see this ringing, plateau, and then charge up. So now I will take my channel 1 and connect it to the drain and source. And I'm going to give a little pressure, make sure I don't think that's on there very well. There we go. Okay, so let's make our trigger point here. And so first thing is, I mean, we can, why did I lose channel 1 when I did that? Did my hand move? Yeah, that's not on there well. Try this one more time. Okay, so let's do a quick stop. Let's just do a screenshot of that. Tag that on Twitch so I can come back and look at it. So this is just overview. We can see that, excuse me, orange trace gate turns on. Yellow trace is our drain. We can see where the transistor turns on because it starts to drop 0 volts since it's dropping the rest across our load. So now we'll zoom in. And this is sort of what I was like getting at earlier. Not sort of, this is exactly what I was getting at earlier, is I want to measure this. So now let's take a quick screenshot of that just so that we got a nice clean one there. And I'm going to turn on cursors. And let's do something real quick. Main zoom, transform, edit. Let's just move this guy over so you can see more of the scope and less of me. So I hit, let's go to cursor. And then I want cursors on, I'm going to put them on channel 3. And if I hit this one, I can move this to, I'm going to use the knob, but I'm just moving that cursor to the trigger point. So this diamond represents the voltage that we triggered at, as well as in time where we triggered. And then I want to grab the other one, so I'm just going to press the cursor knob, and I'm going to move this over. And I don't really know what I'm looking for here. So let's look at this time first. And so what I want to look at is from the time from this moment in time, so from when the load reacts to when the load is, or when the transistor is fully turned on, let's consider that amount of time. And so could I ask somebody in chat to type in the delta difference, which is 114 nanoseconds. And what I'm looking at there is total transistor turn on time. And then if we were to say from the point after it does this, it's 88 nanoseconds. And so let's remember, can you also do 88 nanoseconds? And we'll just have to try to remember what the difference between those two are. What I'm getting at is, I'm not sure what's going on with the ringing, but what I sort of want to say is, okay, after this ringing on both of these, both the gate and the drain occur, it takes 88, 90 nanoseconds for the transistor to fully turn on. So let's do that. Now, so that we don't have to go through this headache again, I'm going to go into reference, and I'm going to say copy channel 1 to R1, and then I'm going to save that to the USB drive. And this is, wrong button. This is the 0 ohm. Channel 1 is 0 ohm drain. Okay. So our oh, that was the comment. Oh, James, you silly guy. Silly guy. Okay, 0 ohm dash drain. Okay. 0 dash drain. I don't know why the file name can only be 8 characters. It supports FAT32. So we'll save that. Okay, so that's saved to our drive. And then we'll change our reference to R3, and we'll load that from channel 3. So we'll say copy that. And then we'll save this one. 0 ohm, enter. The file name, and now we'll do gate. All right, and save that. Think it's your load, struggling to keep 0 ohms when the gate turn comes on. Well, 0 ohms is on the gate, so the load is set to 100 ohms, and so that's not an issue. What we're measuring is what happens when you have no resistance on the gate versus a resistor on the gate. And so what I think is going on is we get a little bit of a ring when the capacitor starts to charge up, and then I'm not sure about this plateau, and then the capacitor charges. And so I think we're actually seeing some inrush limiting occur, but without being able to measure across the current sense resistor, can't verify that. But that's okay, we'll get there. So let's turn this one off and then turn the other reference off. Okay, now we're going to switch to the other board with the 2.2K gate resistor. And then while I do that, just as a reminder, this is, this is the circuit we're looking at, and the only functional difference between the two boards is that the board we just looked at has 0 ohms for this resistor, and this next board has a 3K resistor. So that's off. That's let's turn this off. That can stay on. That's not going to do anything. So we'll move this over to here now. And then do one of these and come over here. Put that in here, and then this and this will come over to here. You know, a couple hours ago when somebody said, you should just solder headers onto those solder pads, and I said, nah, we're just going to make a real quick measurement. This won't be any big thing. Yeah, I should have done what you said, because that would have been really nice if I had soldered those headers on, because then I could just plug the probes in and make life easy. Okay, so let's go back to our scope. Scope, where'd you go? You're over here. First thing, let's make sure we're getting a good gate signal. Turn supply on. Load is ready to go. Run the scope. Okay, so that's good. We got a good signal there. So now we want to do 3K. And just so that in case there's confusion. Okay. All right. Now I will try and touch our drain. And this is where we sort of run into a comparison problem, because okay, yeah, so those time differences are way, way different. I forgot we had changed scales before. Huh. Okay. All right, I'm gonna turn this off because that's driving me crazy. All right, so now so this is where the gate turns on, and then if I went all the way down to here, we're looking at a time of 10 microseconds, and before is, well, yeah, we're in the nanosecond range. So if I move this back to, okay, so it's definitely, I mean, it takes from the time the gate turns on to the time anything happens on the transistor, before the resistor does anything, is a microsecond. I mean, that's pretty significant difference with a 3K resistor versus a 3K versus the 0 ohm. And the other thing is that the gate is way more behaved. We're not getting an inductive spike, or we're not getting, I shouldn't keep calling it inductive. It probably is inductive, but we're not getting a spike on the transistor on the drain when the gate turns on, which is what I expected. I expected the turn on to be much cleaner, but it just takes so much longer. Huh. Okay. So I saved this screenshot. Let's do, I think I want to click out one time because I want to be able to get, I want it to have, and then let's get a shot of this. What I want is, I want to be able to, if I reload these waveforms, I want to have this total turn on time. So let's grab this. And then let's move this back over to when I'm saying it takes this full turn on time. And let's move this over here. I mean, that's not much of it. I mean, it's 1 microsecond difference. Okay, now let's go to the references and save those so that we can reload these later. So let's copy reference 1, save reference, and this is going to be 3K gate. I want to change the comment, and this is actually, it's actually 3.3K, but what's 300 ohms, right? Am I right? Yeah, I thought so. So R1, okay, we'll save that one. And then we'll go to source 3 and go to reference 3, copy that one and save that. And this will be 3K drain. Shoot, I got those backwards. Yep, I did it backwards. Let's not even mess around with that because otherwise I will forget. There is not a problem with the drive. I don't know why you keep saying that. I know for a fact it's fine. Where is... So 3K gate, let's just delete that file. Don't even want to mess around. All right, let's put that back in because R3 is our gate, which is cool. Then we can say enter, save that. How much is the RC constant with those? Great question. Great question. The thing is, the RC constant is going to be, and that's why these behaviors aren't quite what I expected to see. But as I think about it more and more, maybe it is actually how it should be operating. So the RC constant is going to be whatever the resistance value is so that's the R, and then the C is the gate capacitance. And we'll go look back and look at the data sheet here in just a second. So R1 is the drain, yep, for the 3K. So we'll save that. Okay, and then let me turn these references off just so that they don't get confusing. There we go. So if we go and look at the total gate charge, it's not going to be in capacitance, it's going to be in charge, nanocoulombs. So we can do some math and turn that into capacitance. For transconductance, is that the, yeah, this is 24 Siemens. We could use that to figure out what the gate capacitance would be. I thought they just called out gate capacitance. Maybe on different MOSFETs they do. I don't see it here. Unless, yeah, because this is of the drain and the drain. Okay, I thought they just called it out and said the gate capacitance is X. And I don't feel like mathing out what the well, that's something that's gonna be exercise for the reader. So okay. So where we have ended up is we got our MOSFET board working. We're able to make some measurements on it. The one measurement I wanted to make but couldn't is I had wanted to be able to measure the voltage across this current sense resistor, but I wasn't thinking, and I got a current sense resistor that's suitable for a motor and not a gate signal. And so we actually need like a 10 ohm resistor to go here, but I don't have a 10 ohm in this package. So that will have to be another measurement for another time. But I think it will be a good follow-on to what we're seeing, because what we are seeing here is what does the what's going on with the gate, which is the orange, and yellow, which is the drain. And so we're able to actually see how does changing that gate resistance change the turn-on behavior of our MOSFET. And so now it's time to go and try to understand what is causing that to occur. So, as I've said earlier, what I'm going to do is I'm going to throw up in the AddOhms Discord, so addohms.com/discord, that'll redirect you. I'm going to throw up the link to the schematic, which is in KiCad. Maybe I'll put a picture there in case you don't have KiCad, although you should. And then I'll put in these two screenshots we just took, which are the drain and gates on, what do you call it? With 0 ohms on the gate and 3K on the gate. And if you want to provide suggestions or ideas, or you think you know the answer on why these are behaving a little bit different, I would love to hear what you're thinking. So what is this? So this is a MOSFET driver board that we're using to characterize a MOSFET. We did use an Arduino to drive it, but the Arduino is kind of irrelevant in this particular circumstance. So, like I said, if you want to follow more, remember I'm on YouTube as AddOhms, AddOhms. I'm on Twitch as Bald Engineer, which during the week is probably where you're going to find live streams from me. And then I also host a show on Element 14 Presents, which you can find on YouTube by searching for Workbench Wednesdays, where I talk about, shockingly, test equipment that you can find on your workbench. I want to thank everybody in chat who participated, provided some suggestions, asked really good questions. I love that you guys come in and we have these conversations. Let's keep the conversation going on Discord, and I will see you soon. I think the schedule is posted. My next scheduled live stream is going to be Wednesday evening Pacific time. I think I'm doing Wednesday, Friday, and Sunday this week. So thank you, everybody. I will talk to everyone soon, I hope. I got to figure out a better way to close these. All right. Thanks a lot, guys. If you find these videos helpful, please consider supporting AddOhms and the Bald Engineer on Patreon.